All right, so this is going to be a section on the definite integral, which is just a bounded form of the indefinite integral for a function. And so you would actually evaluate it to a number, not have a function out of this integral. And so if you're doing a definite integral, you'll have bounds a and b, which will be the limitations on where on that function you're looking at that you're going to be integrating over. And so if you're doing the integral of a to b of f of x dx, you'll have some number that'll come out. So let's look specifically at how to get this definite integral or how to think about it. And so we can talk a little bit about Riemann's sums. And Riemann's sums are basically rectangles in a region from A to B that's kind of been broken up in different rectangles. And you would take the sum of the height of those functions, or height of that rectangle, times the width of it. And so each of those individual rectangles that you've found the height and width for, you would add up, and then that would be approximately what the area underneath the curve would be. And so let's take a look at what happens if we take the limit as the number of rectangles that we have is broken up into an infinite number of rectangles. So those widths, which were described down here in this sum as a sub I plus 1 minus a sub I for some I, would become infinitesimal. And what I mean by that is they would become so incredibly small that you can't actually tell how large they are. They just basically go down to a point of 0. And so when we're talking about that, that's basically the concept of a differential. So you get this dx for how far you're moving across the actual x-axis with regards to this method of summing up the area. And you would be evaluating what the value of the function is f of x for your f of a sub I at that point. And that ends up turning everything into this nice, neat integral from a to b of your f of x times your dx as you go along that continuum from a to b. And so this is the idea of taking the limit of those in components and going to this continuous integral in that way. So this is more or less kind of a shorthand to kind of show you kind of what's happening when you're doing Riemann sums as they approach the indefinite integral or a definite integral. And so this allows you to kind of see that similarity to summing something up and finding the area underneath the curve. But it's an interesting concept I thought I'd put out there for you guys. And let's talk a little bit about some of the results that you'll get from particular definite integrals. So from a to a of f of x dx, that first integral there is going to be equal to 0. You can also do the integral from a to b of f of x dx. That's going to be equal to negative b to a of f of x dx. So if you switch the bounds from being a to b being b to a for whatever integral you have, then you'll end up with the negative value of that integral. If we're looking at a to b of k times f of x dx, that's equal to k times the integral from a to b of f of x dx. Again, this holds from a similar property as the indefinite integral, where the constant can be pulled out of a definite integral. If we're looking at two functions being added or subtracted from each other and then integrated, we can actually do the integration of each of them separately. That's the next relation that we have there. So that a to b of f of x plus or minus g of x dx is equal to a to b of f of x dx plus or minus a to b of g of x dx. We can also say that if we have bounds going from a to c of f of x dx, that we can find the value of that by finding the integration from a to b of f of x dx plus b to c of f of x dx. You can break up the bounds of integration into two separate integrals and then work with it that way. So that's a potential method that you could use in order to solve something if you weren't able to find it from a value of A to C. You can break it into A to B and B to C and solve each of those individually. All right, so that's been this section on the definite integral. So I'll see you on the next one for the fundamental theorem of calculus.